Yes, let's talk about why AI is never 100% certain. All right. Most times when you use generative AI, for instance, I mean, it's not restricted to only generative AI, but most time when you use generative AI, you have this caveat that, AI can make mistakes because it is never 100% certain. So that's exactly what we are doing here. We want to look at the maths that makes AI not 100% certain. Now, by the end of this lesson, you should be able to explain why AI systems are inherently uncertain, understand the concepts of uncertainty, entropy, and confidence, distinguish between confidence and correctness, interpret probability outputs from AI models, and explain why AI hallucinations occur, understand prediction confidence in practical AI applications, and calculate entropy and confidence using Python. Okay, so let's talk about this. So one of the biggest misconceptions about artificial intelligence is that AI knows the correct answer. That's a huge misconception. Like as you're going to find out more as we go on. In reality, AI almost never knows anything with complete certainty. So instead, modern AI systems estimate probabilities based on patterns learned from data. For example, suppose an AI model is classifying an image. So it sees an image and it says, "Oh, I think it is cat with 92% probability. It is dog with 0.05% probability. It is fox with 0.02% probability and rabbit with 0.01% probability." So the AI predicts cat because it has the highest probability. That it doesn't mean it will be correct, right? But there's every likelihood that it is cat. So, however, notice that the probability is 0.92, not 1.00. So 1.00 is the only guaranteed stuff. So this means that model still believes that there's an 8% chance that another class may be correct, right? So now the question is, why is AI never 100% certain, which this video is all about? So AI systems are statistical models, like we know. I mean, if you've been following from the beginning of this playlist, you know that we said that AI is simply a probability machine. So AI systems are statistical models. So unlike traditional computer programs that follow exact logical rules, AI learns patterns from data. Since data is never perfect, AI predictions are never perfectly certain. So three major sources contribute to uncertainty. You can have data uncertainty, model uncertainty, and inherent randomness. So each source affects how confident an AI system can be. So when the data is uncertain, the model is uncertain, or there is randomness inherent in the data or in the system. So let's talk about data uncertainty now. Training data often contains imperfections such as missing values, incorrect labels, measurement errors, noise, sampling bias. For example, suppose a chest X-ray is accidentally labeled pneumonia, imagine. So even though the patient is healthy, the AI learns from this incorrect example, making future predictions less reliable. And the more noisy the data, the greater the uncertainty you have there. So let's see. Talking about model uncertainty now, no AI model has seen every possible situation. So consider a self-driving car trained mostly on images collected during sunny weather. Okay, so when it encounters snow or heavy rain or thick fog, that can be a problem. So its predictions become less reliable because these situations were underrepresented during the training. And that is why it is better to train models on very robust data. I mean, there's also this issue of photography, right? I mean, I've been in cases where I'm the only black person among many other people, and we are going to take a photograph, and it is dark in the night, so the picture doesn't capture my image, it captures every other person. So the camera has the lens, or so the camera has to be retuned so that I could be captured. So that's the idea of model uncertainty. So this lack of knowledge introduces model uncertainty like that. So and that is why it is important to consider to train every model, any model you want to use on every possibility possible, everything possible like that. Then let's talk about inherent randomness. Some events are naturally unpredictable. That's a sure thing. So examples include stock prices, lottery numbers, earthquakes. Human decisions are totally random. So even if an AI had perfect data, some future events remain fundamentally uncertain. Therefore, uncertainty cannot always be eliminated. So that talks about the idea of inherent randomness. And that is exactly why AI is never 100% certain data and model uncertainty as well as inherent randomness. And then we go ahead to talk about AI thinking in probability. So AI thinks in probabilities. Now, instead of producing definite answers, AI computes probabilities. I mean, we've said that for the umpteenth time. Suppose an email classifier produces this, that a particular email is spam 0.91 probability, and it is not spam with 0.09 probability. Of course, you know they must add up to 1. So the prediction is spam because 0.91 is greater than 0.09. But that's it. But even at that, it's no guarantee. So, however, the AI still acknowledges a 99% chance that the email is actually not spam. So, this probabilistic reasoning is the foundation of modern AI systems. And that is why AI is simply a machine, a probability machine, like we saw in one of the videos, that ChatGPT is just simply a probability machine. Okay, so let me do this. So talking about image classification. Now, suppose an image classifier predicts cat 0.55%. I mean 0.55 probability, dog 0.40, fox 0.05. So the prediction will be cat, right? Uh, because it has the highest probability. Would you trust this prediction? Because dog is also close, right? Probably not, because a confidence of only 55% indicates substantial uncertainty because there is a significant probability that the image may actually be a dog, right? So I mean, it becomes harder because the probabilities are pretty close. And then that takes us to the idea of confidence now. So confidence measures how certain the AI believes its prediction is. So it is usually defined as the highest predicted probability among all possible classes. So if probability of cat is 0.90, so then the model's confidence is 92%. So higher confidence indicates that the model strongly favors one prediction over the others. However, confidence is not a guarantee of correctness. So there's confidence and there's correctness. So the fact that you're confident about something does not mean that you're correct. So, I mean, you can be confident. There have been many cases where I was very confident about things and they actually turned out not to be correct. So confidence does not mean correctness, right? So consider the prediction. If that you have a digit and the probability is that it is 5 is 0.99 and probability that it is 3 is 0.01. So the model predicts 5 with 99% confidence. However, the actual digit is 3. That's very possible. So the model was highly confident but completely wrong. So therefore, high confidence does not imply high accuracy. So confidence reflects the model's belief, not the actual truth, because the model is trained on data, and if it is trained on the wrong data, then of course, it will be very confident on lies, so to speak. So imagine a Python example: computing prediction confidence. Import number as NP because we need it here to declare an array. So you have classes cat, dog, and fox, and then you have probabilities. Probability cat 0.55, dog 0.40, fox 0.05. I think the same one we had up somewhere. Yeah, that's here now. So we are bringing it here. So the prediction now, classes, yeah, we want to predict classes. So you have np.argmax of the probabilities. So you want to have that kind of prediction. Then the confidence, you have probabilities. You take the maximum probability. So you have the prediction to be cat. By the time you run this, the prediction comes out as cat, and the confidence is 55, 0.5, but that's 55. You have 55% confidence that it is cat, but that's not good enough, so to speak. And that takes us to the idea of entropy. We are talking about why AI is never 100% certain. Entropy now, confidence tells us how strongly the model believes its best prediction. That's confidence there. Entropy measures the overall uncertainty of the entire probability distribution. So the entire probability distribution there, the entropy measures how the overall uncertainty. So if one class dominates, the entropy is low. But if several classes have similar probability, the entropy is high. So entropy is widely used in information theory and machine learning. And of course, it's entropy that makes creativity and variety possible in AI, right? So let's talk about the entropy formula. It's a very popular formula as propounded by Shannon, who was one of the pioneers of information theory. So let's look at the entropy formula. For a probability distribution P1, P2 up to Pn, entropy is defined as H, which is equal to minus summation from I equals 1 to n of each of the PIs. So P1, P2, so PI log to base 2 of PI, where H is entropy, PI is the probability of class I. So the interpretation is that when H equal to 0 means complete certainty, that you are very sure there's no disorderliness in your prediction. That is perfect. So H equals 0 means probability of 1. Then higher entropy indicates greater uncertainty, while maximum entropy occurs when all classes are equally likely. So if the probability that a particular image is either cat, dog, or fox, at maybe 0.33% each, or roughly that, maybe 33, 33, 34. So in that case, you have maximum entropy when all classes are equally likely. So then we have our example one. Suppose that you have a class, cat, dog, and probability 0.9 and 0.01. Since almost all probability is concentrated in one class, so almost all the probability is concentrated on cats. So the entropy is very small. So there's a low level of disorderliness. So this indicates that the model is highly certain that this is cat, of course, with a 1% chance that it may not be cat. Then you have example two. If you now suppose that cat is 0.50 probability and dog is 0.50 probability. So the probabilities are evenly distributed. The model cannot decide whether between the two classes. Therefore, the entropy is much larger. So this represents maximum uncertainty for two classes, right? So there's equal chance of it being either cat or dog. So in this case now, if you come on here, so import, I mean, by an example, you want to calculate entropy. So import number as NP because we need to declare array here. So define the entropy of probabilities. So don't forget, I think this is still connected to what we had here before. These probabilities, we have a 0.55 and all this. So we define all of that. And then you now define a function, entropy of probabilities. Oh, okay. Now it's not connected to that. You have to supply your probability here. So probabilities now np dot array of probabilities, and then you have probabilities now equals probabilities where probability is greater than zero, and then you return minus np dot sum. So that's formula for entropy now. Sum of probabilities multiplied by the np dot log 2 of probabilities now. So if you now print entropy 0.99, 0.01, so this is your probability distribution now. And then if you print the entropy, so the entropy for this is very low, because there's higher certainty. The entropy for this one is very high because you have a 50-50 chance like that. You could also do it for an array that is more than two, as far as they all add up to one. So imagine here you now have 0.55, okay, 0.55, then you now have 0.30, and then you now have 0.15. So the entropy may be somewhere in between 0.08 and 1.0 because there's a fair distribution here. So you see the entropy is pretty high here. Okay, 4555, yeah. So the entropy now is 1.4 something something. So it's even higher than what we have here. So like that. So there's higher disorderliness there. Okay, so we move on to visualize. How do you visualize entropy now? So import number as NP because you want a number here. Then you have your you have entropy formula here, and then you plot probability of class A, entropy in bits, and entropy of binary classifier. So you run that and you get this. You have entropy of a binary classifier. So probability of class A and the entropy right here. So this is the kind of thing. Yeah. So when the entropy is zero, right? You have the probability is also low. But you have maximum entropy around somewhere when there's equal distribution, and then it goes higher at this other end, like we saw before. So entropy becomes higher when there's even distribution. So interpreting the entropy curve now, observe the following. Entropy is the smallest when one probability is close to 0 or 1. So you have smallest entropy when you have one probability close to 0 or 1. Okay. Then entropy reaches its maximum, somewhere around here where it's around 0.5 so average there. So entropy reaches its maximum when P is 0.5 because the model is equally uncertain between both classes. Then the entropy curve therefore provides a quantitative measure of uncertainty like that. And then we go on to talk about confidence versus entropy. So although related, confidence and entropy measure different aspects of prediction quality. For instance, if you have these probabilities now 0.99 and 0.01, the confidence is 99%, as you can see, but the entropy is very low because high confidence means low entropy. So the interpretation means that the model is very certain about its prediction. Then if you have 0.90 and 0.1, the confidence is 90%. The entropy maybe not very low, but it is quite low. And it means the model is fairly certain by way of interpretation. And then you have probability 0.7, 0.3. The confidence is 70%. So the entropy is moderate and interpretation with some uncertainty. Then 0.5 and 0.4, and that's equally likely. So confidence is 51%. So the entropy is high and there's highly so the model is highly uncertain. And if you have 0.34, 0.33, 0.33, like I said the other time, the confidence is the highest one here. That's 34%. The entropy is very high and the interpretation means there's high uncertainty. So confidence considers only the largest probability, and entropy considers the entire probability distribution, how they are distributed, right? So if you want to consider the entire probability, entropy may be a good measure for you. So it all depends on what you want. So let's go ahead and talk about hallucinations, which is a common term when we talk about AI, especially yeah, AI in general, especially generative AI and all that. So a hallucination occurs when an AI generates information that appears convincing but is actually false. Like you have cases of AI generating papers that were never published. So to make up a full citation that was not published. For example, user types who won the Nobel Prize in Physics in 2050. And since this event has not happened, a language model may invent a person's name instead of admitting uncertainty. So this fabricated answer is called a hallucination. Of course, with as the AI models advance, hallucination becomes lower and lower, but this is still a possibility, right? So, I mean, in the early days of ChatGPT, to tell you if you need references, it will make up the references for you that do not exist. So, why hallucinations occur? Large language models generate text by predicting the most likely next word. All right. So, they are not inherently fact-checking systems. So, hallucinations occur because the required information may not exist. The model may have incomplete knowledge. The model predicts plausible text rather than verified facts. The probability distributions may strongly favor and incorrect continuation. Therefore, fluent language does not necessarily imply factual correctness. Okay, somebody may be saying gibberish with confidence. So that's the idea of hallucination. So prediction confidence now. Many AI systems report confidence scores together with predictions. Examples for face recognition, there's 90, say you have 99.3%. That disease diagnosis, you have 81%. Object detection, 94%. Speech cognition, recognition rather, you have 88%. Confidence helps users decide whether an AI prediction should be trusted or reviewed by a human expert. So, and then we have ideas about confidence thresholds. Many AI systems use decision thresholds. For example, confidence greater than or equal to 0.90 can mean accept automatically. But when the confidence is less than 0.90, you can request human review. So thresholds are especially important in safety critical applications such as medicine, aviation, and autonomous vehicles. So the threshold depends on the cost of making an incorrect prediction. So you need to have, depending on the system you're working in, you want to check for confidence thresholds. So imagine Python confidence threshold. Now, a prediction is made that a particular case of an X-ray is pneumonia, and the confidence is 0.58 and the threshold is 0.9. So if confidence is greater than threshold, like here, confidence is not greater than threshold. If confidence is greater than threshold, then accept prediction. Else, print human review required. So in this case, now confidence is lower than threshold. So human review will be required, if you run this system. So you need this. This is the kind of things you have when you talk about quality control. So you want to check the confidence against this threshold. So a well-calibrated AI system produces confidence scores that match its long-term accuracy. For example, if the model predicts with 90% confidence on many different cases, it should be correct approximately 90% of the time. So poor calibration leads to overconfidence or even underconfidence, and both can reduce user trust and increase decision-making risk. So let's talk about real-world applications. First of all, we talk about autonomous vehicles. So if an object detector predicts pedestrian 0.52, so a self-driving car, for instance, sees a pedestrian with probability 0.52 and a cyclist with probability 0.48. The vehicle should slow down because the prediction is uncertain. So the vehicle has to slow down. But if it can predict that, that if it can predict with higher probability, so it's easier to know what to do in that case. Then in medical diagnosis, if AI predicts disease to be pneumonia with probability 0.40 and tuberculosis 0.35, lung cancer 0.5. So physicians should combine these probabilities with laboratory tests and patient history before making a diagnosis because there's no guarantee of anything because the probabilities are sort of close, just between this and this, that's 0.05. Between pneumonia and tuberculosis, between tuberculosis and lung cancer, that's just 0.1. So human check is important, especially when it involves medicine. It involves a human life. So if the probability of fraud is 0.96, for instance, the bank may temporarily block the transaction and request additional verification. It may not be fraud, right? But I mean, 0.96 is too high that you want to block the transaction and really be sure what's happening. Then we have our key takeaways now. We see that AI systems are probabilistic rather than perfectly certain, and uncertainty arises from imperfect data, limited models, and randomness, like we saw before. Then confidence measures belief in the most likely prediction. Entropy measures uncertainty across the entire probability distribution. So high confidence does not guarantee correctness, like we've seen already. Then hallucinations occur because language models generate plausible text rather than verified facts. So confidence scores help determine when human oversight is necessary. Understanding uncertainty is essential for deploying trustworthy AI systems. And that goes why AI is 100% not correct, is not 100%, is never 100% certain at any point in time. So we come to our practice problems. So as usual, we have 20 of them, and I'll be solving two of them. So I'll be solving 15 and 20, but let's just see all the problems. So here you have 1 to 3 all clear, 1 to 3 clear. Then you have 4 to 7, 4 to 7 clear. Then 8 to you can see 8 to 13. You can see a part of 14, right? So let's just say 8 to 13. Then 14 to say 14 to 18 all clear. Then I'll be solving 15, right? Rank the following probability distribution from lowest entropy to highest entropy. Okay, so we have to do the computations. Then I'll be solving 20 also. Suppose you are designing an AI system for aircraft engine fault detection. Discuss how uncertainty, entropy, confidence, and human oversight should work together to minimize safety risks. So I'll be dealing with 15, this 15 here, and 20. So let's go for that, shall we? Okay. So question problem 15 to start. Let's start with problem 15. Problem 15. Yeah, so problem 15 now. Oh, okay. Oh, I think I was looking at another one. So I'll be solving 3 and 20 here. Sorry, 3 and 20. 3 and 20. Let's go back and see. 3, this is 3. Yeah. Compute the entropy of the probability distribution this using this now. That's 3. And then we'll be dealing with 20, like I said before. So 20 remains 3 and 20. So let's go. Problem 3 and problem 20. So let's talk about problem. Okay, I guess I want to change this. Problem 3. So we want to compute the entropy, compute the entropy of the probability distribution 0.80 and 0.20 using H, which is minus summation over I, pi log to base 2 of p sub I, like that. So let's go and do that. Let's say we have step, so in step 1 now, step 1, we write the entropy formula, the entropy formula, write the entropy formula. So here you have H to be minus 0.80 log to base 2, log to base 2 of 0.80 plus 0.20 log to base 2 of 0.20. So all of that. So we have h now equals minus 0.80 log 8 0.8 to base 2 is minus 0.3219 plus 0.20 into log 0.2 to base 2, that is minus 2.3219. Oh, seriously, they have the same logarithm? Okay, not exactly the same. Okay, minus 0.321, and this is minus 2.321. Okay, okay, get it. So now we obtain h to be, we have h to be minus, so if you multiply these two now, we have minus 0.2575. Then here, this will also be minus. So this is minus 0.4644 there. Then we then have h to be minus. So inside here, we have 0 point minus 0.7219. So that h then, the entropy is overall 0.7219 bits. And that goes like that. Okay. So we can have h to be approximately 0.722 bits. That is the entropy. So this is a very high entropy, by the way. This is 72% entropy. So that's pretty high. So the interpretation then, so to interpret this, right? An entropy of approximately 0.722 bits indicates moderate uncertainty. Moderate uncertainty. So the model, okay, I said it's high, it's moderate. I think this is not percent per se, right? So the model, so this, we can't convert this to percentage, mind you, so it's moderate, just not percent, sorry. So the model is fairly fairly confident. It's fairly confident because one class, one class, which is 80%, is is much more is much more likely than the other, which is 20%. But there is still some uncertainty. And that's how that goes. So we come on to problem 20 now. So problem 20, problem 20. Suppose you are designing an AI system, an AI system for aircraft, an AI system for aircraft engine fault detection. Discuss discuss how uncertainty, entropy, confidence, and human oversight and human oversight should should work together should work together to minimize safety risks. So the solution now. So first of all, right, we know that aircraft engine fault detection, aircraft engine fault detection is a safety critical application. So that's, I mean, it requires serious attention. So it's a safety critical application. That's the first point, very important. And as a result of that, an an incorrect prediction, an incorrect prediction could lead to unnecessary unnecessary maintenance, unnecessary maintenance, costly flight delays, costly flight delays, or even catastrophic accidents, even catastrophic accidents. Therefore, therefore, AI predictions, AI predictions should should never be accepted, should never be accepted solely because they have the highest probability. So the key word here is this safety critical application. So it's safety critical. So as a result of that, even high predictions would not be enough for you to accept anything. So then that goes ahead. So you know, we are told to discuss things bordering on uncertainty, entropy, and confidence, and as well as human oversight. So four things. So let's start one after the other. First of all, let's talk about uncertainty. Uncertainty. So here, the AI, the AI should, the AI should estimate the uncertainty of every prediction, of every prediction. And in doing that, we see that high uncertainty, high uncertainty may occur because of one, noisy, noisy sensor readings, noisy sensor readings. You know, we're talking about aircraft. Then we can have incomplete maintenance records, incomplete maintenance records. Then unusual engine behavior, unusual engine behavior. Then you have environmental conditions not seen during training. Environmental conditions, that's inherent randomness, right? Environmental conditions not seen during training. So here that we see that when when uncertainty is high, the system should avoid making Automatic maintenance decisions. Automatic maintenance decisions. So we have that. Then number two, we talk about confidence. So we talk about confidence. So talking about confidence, the AI should report, AI should report a confidence score, a confidence score for every detected fault. Of course, that's baseline for every detected fault. Very important. For example, if you have a fault like this fault of turbine blade damage, blade damage, turbine blade damage, and the confidence is 0.97, like this. So a confidence, of 97% indicates the model strongly favors this diagnosis. However, 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 confidence alone, confidence alone should not determine, should not determine the final decision. The final decision, because a highly confident, a highly confident prediction can still be incorrect, can still be incorrect. Yeah, that talks about confidence. Then we'll move on to entropy, which is number three. Entropy. Entropy talks about uncertainty. So entropy provides an overall measure of prediction uncertainty. Prediction uncertainty. For example, so imagine fault and probability. So you have compressor wear, compressor wear, 0.35 probability, and then you have turbine crack, turbine crack, 0.34, pretty close. And then you have bearing failure, bearing failure, that's 0.31, all pretty close. Okay, what do you do with that? Although the highest confidence, the highest confidence is 35%. The highest confidence is 35%. The probabilities the probabilities are very similar. This results in high entropy, indicating that the model is uncertain about the true fault, about the true fault. So high entropy should trigger, high entropy should trigger additional inspections. Okay, so that takes us to the fourth one, which is human oversight. Human oversight. Okay, so talking about human oversight, right? A a certified aircraft engineer, a certified aircraft engineer should review predictions, should review predictions whenever one, confidence is below a predefined threshold. Two, entropy is high. Entropy is high. Three, sensor data are incomplete. Four, the prediction could affect flight safety. So then the engineer may inspect additional sensor readings, maintenance history, vibration analysis, because you have moving parts, right? Vibration analysis, or physical engine components before making the final decision. Okay, so let's talk about recommended decision policy, right? So recommended decision policy. So imagine you have okay, let me go back here. So imagine the confidence, the entropy, and what action should you take? So here, when the confidence is high, right? And the entropy is low, so you can accept AI recommendation, accept AI recommendation after routine verification. Okay, so that's that. Then next, what if confidence is high and entropy is also high? So because of high entropy, that's quite a challenge. So high entropy means high uncertainty. So you have to perform additional perform additional diagnostic tests, diagnostic tests. Again, what if confidence is low and entropy is also low? Low entropy means low uncertainty, but then low confidence is also something of concern. So you want to gather more evidence before deciding. Gather more evidence before deciding. And the concern here is about the low confidence. Then we have what if the confidence is low and entropy is high? That's big, that's actually big trouble. So you have to this immediate require expert review. Require immediate expert review. So the most desirable case is high confidence, low entropy. Okay, high confidence, low entropy. Just do routine check and keep going. Okay, so can we conclude then? Conclusion. So conclusion, a safe aircraft, okay. In conclusion, a safe aircraft, a safe aircraft detection, fault detection system, okay, should combine, the following. One, confidence, confidence measure, to measure how strongly, how strongly the AI favors a prediction. Okay, so confidence is important there. Then two, entropy. It requires it should combine entropy now to measure measure overall uncertainty, overall uncertainty. Then you also it also needs to talk about uncertainty estimate. Uncertainty estimates key to identify identify unreliable situations, situations, and human oversight. So human oversight. So at the end of the day, it's human machine combination, human oversight for all safety critical applications. Safety critical, because safety is of serious importance. Safety critical decisions. So using using these four components together, using these four components together produces a far more reliable, a far more reliable and trustworthy, trustworthy AI system than relying on prediction confidence alone, than relying on prediction confidence alone. Okay. So we have to combine these four critical things. Very important to so that we to have a safe system, uncertainty, entropy, confidence, and human oversight. So let's go on and flash the questions again. So again, these are the practice problems I've done, 15 and 20, I think. I've done 3 and 20 rather. So see 1 to 3 here clearly. 1 to 3, then 4 to 8, 4 to 8 here, then 9 to 9 to 14 here, 9 to 14, then 15 to okay, 15 to 18, kind of 15 to 18, and the rest. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to my channel already, I thank you very much for doing that. And if you have not, this is the right time to go ahead and subscribe. Also, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, and that gives you some special privileges you find out when you click on join. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right. Bye.